Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 4. Section 1, Chapter 6, Topic 4. Predicting Crack Initiation and Growth in Semiconductor Packaging. Introduction. Crack initiation and growth are critical phenomena in semiconductor packaging, significantly impacting the reliability and longevity of electronic devices. Understanding the factors influencing crack initiation and growth is essential for predicting failure modes, optimizing package design, and enhancing reliability. This overview delves into the mechanisms of crack initiation and growth in semiconductor packaging, explores predictive models and simulation techniques, and discusses strategies for mitigating crack propagation. Mechanisms of crack initiation and growth. Crack initiation and growth in semiconductor packaging can occur through various mechanisms. Mechanical stresses. Mechanical loading, such as thermal cycling, mechanical shock, vibration, or bending, can induce stresses that exceed the material's yield strength, leading to crack initiation at stress concentration sites. Thermal mismatch. Differential thermal expansion coefficients between materials, such as dye, substrate, and encapsulant, can generate thermal stresses during temperature cycling, promoting crack initiation at interfaces. Material defects. Material defects, such as voids, inclusions, microcracks, or residual stresses introduced during manufacturing processes, can act as nucleation sites for crack initiation and propagation. Environmental factors. Exposure to environmental factors, such as moisture, humidity, chemicals, or corrosive agents, can accelerate material degradation, weaken interfaces, and promote crack growth over time. Electromigration. Electromigration-induced diffusion of atoms in conductive lines or interconnects can lead to void formation, hillock growth, and crack initiation, compromising electrical conductivity and reliability. Fatigue loading. Cyclic mechanical loading, thermal cycling, or electrical cycling can induce fatigue damage, including microcrack nucleation and propagation, ultimately leading to catastrophic failure. Predictive models and simulation techniques. Predicting crack initiation and growth in semiconductor packaging involves various analytical and computational methods. Fracture mechanics. Fracture mechanics principles, such as linear elastic fracture mechanics, LEFM, and nonlinear fracture mechanics, provide analytical models for predicting crack propagation based on stress intensity factors, energy release rates, and material properties. Finite Element Analysis (FE). Finite element analysis simulates stress distributions, deformation behaviors, and crack propagation paths in semiconductor packages under mechanical, thermal, or environmental loading conditions. Cohesive zone modeling (CZM). Cohesive zone modeling characterizes the cohesive behavior of interfaces and materials, allowing for the simulation of crack initiation, propagation, and interaction at microscale and macroscale levels. Extended Finite Element Method (XFEM). XFEM extends the capabilities of traditional FE by incorporating discontinuities, such as cracks, interfaces, or material interfaces, into the finite element mesh, enabling accurate simulation of crack propagation without remeshing. Damage mechanics. Damage mechanics models quantify material damage evolution, including microcrack initiation, growth, and coalescence, under cyclic loading, creep, or fatigue conditions. Phase field modeling. Phase field modeling describes crack propagation as a continuous phase field variable, capturing crack nucleation, propagation, and branching with diffuse interfaces and without predefined crack paths. Strategies for mitigating crack propagation. To mitigate crack propagation and enhance the reliability of semiconductor packaging, several strategies can be employed. Material selection. Choose materials with high fracture toughness, low coefficient of thermal expansion, CTE, and good adhesion strength to minimize crack initiation and propagation. Design optimization. Redesign package layouts, geometries, and structures to reduce stress concentrations, improve load distribution, and enhance fracture resistance. Stress relief. Incorporate stress relief features, such as fillets, notches, or compliant layers, to redistribute stresses and reduce stress concentrations in critical regions of semiconductor packages. Interface engineering. Enhance interface adhesion, compatibility, and robustness through surface treatments, adhesion promoters, or interfacial layers to prevent crack initiation and propagation. Packaging techniques. Implement advanced packaging techniques, such as underfilling, encapsulation, or reinforcement, to encapsulate components, redistribute stresses, and prevent crack propagation. Reliability testing. Conduct accelerated aging tests, mechanical stress tests, and environmental exposure tests to identify weak points, assess package performance, and validate mitigation strategies for crack propagation. Conclusion. Predicting crack initiation and growth is essential for ensuring the reliability, durability, and performance of semiconductor packaging. By understanding the mechanisms of crack initiation and growth, utilizing predictive models and simulation techniques, and implementing strategies for mitigating crack propagation, engineers can optimize package design, enhance material selection, and improve reliability testing to mitigate failure risks and extend the lifespan of electronic devices. Continued research and development in fracture mechanics, computational modeling, and reliability assessment will further advance semiconductor packaging technology and drive innovation in electronic packaging solutions. Thanks for watching. Please like, share, and subscribe.